Yeah, it
I
does.
think it does. Okay, very
Mhm.
good. Thank you. G is a finite group, and it acts on finitely generated mm, commutative uh, algebra A, uh, and then we can form the subalgebra of G invariants. We discussed it a little bit last time. Um, so we want to prove today uh, the following theorem one, that the algebra of invariants is also finitely generated. Okay, so this is at least a particular case of this famous Hilbert theorem I referred to last time. And the proof is pretty long. It uses a few steps. So the first step is the particular case of so-called Reynolds operator, projector, or in more down-to-earth terms, averaging.
Миша, а над каким полем
Yeah.
мы?
Oh yes, that's a good thing. Thank you, Dima, for recalling this. Last time we assumed that we will always be working over field of complex numbers. So I don't know where to write it. So everything is sorry, is over complex numbers throughout the whole course. Okay. So this averaging operator, this will crucially use the finiteness of group G. So it's an operator alpha from A to itself, and alpha of A is 1 over the order of G, the sum over all the elements in G, GA, like this. So this is a linear operator with the following basic properties. First, the image of alpha lies in the space of invariant. This is clear. Second, it is sort of linear, namely alpha of the product AB is A times alpha of B if A is already invariant and B is arbitrary. We'll prove this momentarily. And the third property is a sort of factoriality or naturality. With respect to homomorphisms. Of algebras. So if we have a homomorphism phi from A1 to A2, then then phi of alpha of A equals alpha of phi of A for any A in A1. Okay, this is also clear. And let's prove 2. Alpha of AB equals 1 over the order of G, sum over all elements in our finite group, G of AB. And now we use that G acts by automorphisms. So this is 1 over the order of G, the sum of GA times GB, since A is invariant. Okay, so this will be 1 over the order of G, the sum of A, G of B, and this will be A alpha of B. Okay, so this is clear. Now we can formulate the following corollary. That if we have a surjective homomorphism of algebras, homomorphism, then the induced map on the invariant is also surjective. Okay, this is immediately clear. And now we will need the next step. It's a proposition 1. So let I be an ideal in the algebra of invariants. Then we can generate by this ideal the ideal in the algebra, in the ambient algebra A. Okay, and then we can take this ideal generated in the ambient algebra A and intersect it with our subalgebra of invariant. And then the claim is that we obtain our initial ideal I. Okay. The proof is not difficult. So we take an element in the ideal. Sorry, we take an invariant element that lies in the generated ideal. So assume A lies in AI. Okay, well, what does it mean? It means that there are some elements A1 and so on, AK in the ideal I, and elements B1 and so on, BK in the algebra A, such that A is the sum of AI, BI. Okay, but then it means that A is the sum of the averaging operators AI alpha of BI, right? Because these A's they lie in the ideal inside the invariant algebra, okay? And this Reynolds operator is linear over the invariance. Okay, so this lies in the ideal. And there we are. Okay. So Okay. Okay, so the second corollary from this is that I is finitely generated as an ideal. Indeed. We recall that our algebra A was assumed to be finally generated, right, from the very beginning. So by the Hilbert-Bayes theorem, A is Noetherian, and it means that for any ideal J in A, it is finitely generated. So there is a finite generating subset, say, maybe let me maybe let me say it this way. For any ideal and a generating set F inside the ideal, there is a finite generating subset F naught inside F. Okay, now this is just a formulation of Noetherian property. Okay, so now let's take the ideal J that is generated by our ideal I inside the invariant subalgebra, and let's take F just as the whole set I. Clearly, it generates, but now inside this set I, we can find a finite subset. F not inside I. Okay, and now let I not inside the invariant subalgebra be the ideal generated by F naught. Right? Okay. Then we know that A I naught is A I, and hence I naught is the intersection A I naught with the invariant subalgebra, and this is just AI intersection with invariant subalgebra, and this is just I. Fine. So I is generated by F naught, and it is finitely generated, and the corollary is proved. So I is generated by F naught, and we are done. Okay, and now we're almost done. We know that the subalgebra of invariance is Noetherian. Okay, but unfortunately, this does not necessarily imply that it is finally generated. If it is finally generated, it is Noetherian, but not vice versa in general. So we will need some extra work. So we need something else. Namely, if we know some additional assumption, that a G, for example, is graded, and even maybe positively graded, then Noetherian property it does imply finite generation. So let me explain this in detail. So we consider some algebra B, again, B, the commutative algebra. And it is graded. Now, n is a non-negative number, and B0 is just complex numbers. So in degree 0, I have complex numbers. In negative degrees, I have nothing. And then you have something in the positive degrees. So it's called positively graded.
Что-то конечномерное?
Not necessarily. Well, if I assume finite generation, they will be necessarily finite dimensional. But in general, positively graded algebra does not have to have finite graded pieces. Okay, and well, certainly Bi times Bj lies in Bi plus j, and then our next proposition is that the properties B is Noetherian, and B is finitely generated. Oops, sorry, where I am. Sorry. So these properties are equivalent. Okay. Now, certainly, the finite generation implies Noetherian property. This is known by Hilbert. So B implies A by Hilbert. Basis theorem. And when I prove the converse, so let B1 and so on, Bk, be the generators of the augmentation ideal be greater than 0. So this is the direct sum over all, so sorry, strictly positive n of Bn. Okay, then I claim that they are actually the generators of the algebra. The whole algebra. Let's see this. So otherwise, take some element B, not generated by B1 and so on, Bk, of the smallest degree. And by the way, we can also, we assume that all BIs are homogeneous. Namely, if they are not, we just take their homogeneous components and add them to the generating set. Okay. So we know that B necessarily lies in the augmentation ideal, B positive, and so it can be expressed via these generators of ideal. So there are C1, so on, Ck, such that the element B is the sum of Bi, Ci. But since B is homogeneous, these Ci's are also homogeneous, and the degrees sum up like this. So it means that the degrees of Ci's are strictly less than the degree of B. And hence, by our assumption that B had the smallest degree, all Ci's are expressible through BIs. Like this. And hence, B itself also is expressible through BIs. Okay, there we are. Okay, so for example, the corollary 3. If our initial algebra A was just polynomials in some vector space, in particular graded, hence the invariant subalgebra is also graded. And we proved it Noetherian, and now it follows that it is also finitely generated. Okay. So now we want to prove this without the graded assumption, just as in theorem 1. So we're almost ready to prove theorem 1, and it will follow from the next proposition 3, that there is an epimorphism from some symmetric algebra onto A. And this is evident because A was supposed to be finite generated, right? The point is that this epimorphism is G equivariant. Okay, so we can find a vector space with action of G and a surjection from polynomials in V star onto A. For some G module V. Okay. So this proposition immediately implies theorem 1, right? Because we had this the first corollary claimed that the surjection on algebras induces the surjection on invariant subalgebras. Okay, so it now I have to prove this proposition. And to this end, we need some notation or definition. Let say U be a G module, but well, maybe in the statement of proposition 3, I assumed that this G module V was finite dimensional. Well, let me write it down. Dimensional G module V, and now this U is not necessarily finite dimensional, some arbitrary G module. Okay, but we say that U is locally finite. If any element vector here is contained in a finite dimensional G submodule. Okay. So for a finite group G, any U is locally finite. Namely, given a vector U, just take the span of G U over all elements of our finite group. Okay. In fact, the theorem we're proving today will be equally true for all the reductive groups, so say classical groups like GL or SO or SP. But the proof will be somewhat different, but the key steps will be the same. In particular, we will be able to prove that any algebraic representation of a reductive group is locally finite. And in this argument, in the proof of proposition 3, I will only use this locally finiteness property, nothing else. Okay. So let me just restate it. Proposition 3 prime. That if the action of G on A is locally finite, then there is a finite dimensional G module V with rejection from polynomials in V star onto A, G equivariant. Okay, so that's what we need to prove. And now take some generating set of algebra A. And for each of them, take a finite dimensional subset, UI containing AI finite dimensional invariant subset. And say take U tilde is the sum of all these UIs. It is also finite dimensional and G invariant. And now certainly the symmetric algebra of U tilde now surjects onto A. So we can take V is U tilde dual. There we are. So now the theorem 1 is proved. And just let me repeat once again what I already said, that we somehow deduced our proof of theorem 1 from two formal properties. Of the action of G on A. Namely, the first was the existence of the Reynolds projector. Alpha from A to the sub algebra of invariance. And second, the local finiteness of the action of G on A. Okay, so later on, we will establish these properties for all the reductive groups G. And this is actually what Hilbert did. So this was his famous theorem of 1890. Okay. So now we can continue with an even more classical theorem due to Noether. So now G is again a finite group, and V is its finite dimensional representation. Then I claim that the algebra of invariants is generated in degrees less than or equal to the order of G. Okay. And then eventually you will have a home assignment problem to give an example when this degree is actually reached, that you cannot generate the invariance in smaller degrees. But if you have looked at the first home assignment, then it is about exactly this situation. We have a finite subgroup acting on two-dimensional representation, and there you have invariants generated in pretty high degrees, but still they are smaller than the order of this group. For example, there is a icosahedron group of order 60 or maybe 120, and the invariants have smaller degrees. Okay, so let's prove this. And the proof is not very difficult. It goes somehow in two steps. First, you generate all the polynomials just by the powers and just by polarization, and then you express the invariant sum of powers from the elementary symmetric polynomials, and those have small degrees. Okay, so this algebra of polynomials is spanned by the powers. So U is covector, and K is some positive number, and spanned as a vector space. Then not just generated as algebra, but spanned as a vector space. It's called polarization. So the invariants are also spanned as a vector space by Reynolds projectors of U to the power K. U is a covector, K is a positive number. And given such U, we denote its images G1U and so on, G and U by, say, X1 and so on, Xn. And so here N is the order of our group. So the Reynolds projector of U to the power K will be 1 over the order of G, the sum from 1 to N of the powers of these elements. And it is a symmetric polynomial in X1 and so on, Xn. And now all the symmetric polynomials can be expressed via the elementary symmetric polynomials. E1 and so on, En. Okay, so these are sums of products, yeah, of different elements among x1, so on, xn, and hence all these polynomials are G invariant, right? Because the variables x are just GU, right? And when you multiply by some G, it amounts just to permuting those x's. Okay, and there we are. Since we know now that the degree of EI is I, and hence degrees of all those polynomials are elementary symmetric polynomials are at most the order of the group. But we know that they generate everything. Okay. So any element in the invariance lies in a subalgebra generated by invariance of degree less than or equal to the order of the group. And that's what we wanted to prove. Okay. So now let us prove the next proposition. That under the assumptions of theorem 1, so finite group G acts on finite generated algebra A. This algebra A is finite as a module over its invariance. Okay, and the proof is immediate from some basic commutative algebra. So we know that A is finitely generated. It suffices to check that all the generators are integral over the subalgebra of invariance. Okay. In fact, any element is integral. So take element A in our algebra and consider the polynomial equation f of x. With coefficients in algebra A. And this is the product over all elements in G of x minus GA. Okay, and then clearly it has coefficients actually in the invariant subalgebra, and the leading coefficient is 1. and A is a root. There we are. So any element of A is integral over the invariant. Fine. Now we'll apply this proposition 4 to some geometric. So we will somehow. I will explain a geometric interpretation of this proposition. So now assume that A has no nilpotence. So A is the algebra of functions on some affine algebraic variety. This is the spectrum of A. And the action of G on A gives rise to the action of G on this variety X, and vice versa. So it's equivalent to giving the action on X, algebraic action. So we just define the quotient X modulo G as the spectrum of the algebra of invariants. Okay, now I will explain that this is really what you would hope the quotient to be, namely that it classifies the orbits of G in the space X. But just to begin with, we define this quotient as an algebraic variety, the spectrum of the algebra of invariants. Okay, so now the embedding of the invariant subalgebra into A gives rise to a morphism pi from X to X modulo G. And certainly this morphism is G equivariant. Okay, and now we prove the third theorem, namely that pi is surjective, and its fibers are exactly the G orbits on X. So in other words, this is exactly what one would expect this quotient to be. And so in this case, when I have the action of a finite group on an algebraic variety, the naive quotient makes sense, and it's another algebraic variety. The quotient morphism just glues the orbit. Okay, so let's prove this theorem. First, we'll prove the surjectivity.
Но это только для афинных, да?
Oh yes. We consider only the affine algebraic varieties over complex numbers and only finite groups so far. Then later on we'll move to more advanced cases, but so far just affine algebraic variety and finite groups.
Отсутствие нильпотентов — это содержательное условие или, ну, можно предположить, что...
I want to work with algebraic varieties, so otherwise I somehow won't know what to say. but certainly we can form the so-called categorical quotient. That's what we're doing. But if I want to formulate its geometric meaning, I'd rather stick to algebraic varieties. Okay. So we start with surjectivity. Of this projection pi, and let me give two arguments for this. So first, pi is dominant, since we have an embedding of invariance into A, and also we know that pi is finite, since A is a finite AG module. And now this implies that pi is surjective. Here is some abstract argument from commutative algebra. So I guess some may be dissatisfied with it. Let me give another argument as a corollary of proposition 1. We will deduce it from proposition 1. Namely, let's take a point x in the quotient space. This corresponds to some maximal ideal M in the invariant algebra. And the property that this x lies in the image, that the preimage of x is not empty, means that this maximal ideal inside A generates another maximal ideal, that it is not the whole algebra A. Okay, but we know that the intersection of the ideal generated by M with the invariant algebra is this original ideal M. So it implies that the ideal generated by M cannot be the whole algebra A. Okay, there we are. Now, so we proved surjectivity of pi, and now we have to study its fibers. So let's prove some general lemma. So let y1 and y2 in X be two closed G invariant subvarieties. Okay, so we assume that they do not intersect. And then their images do not intersect either. So let's prove this. Since they do not intersect, it means that the functions on their union are just the direct sum of functions on them on a y1 and y2. Okay. So this is another closed subvariety of X. And this means a surjection from the ring of functions on X onto the ring of functions on the union y1 and y2. And in particular, we can find a function on X such that f restricted to y1 is identically 1, and f restricted to y2 is identically 0. Okay, and now let us apply the Reynolds projector to this function. So alpha f, and then we see that there's an invariant function. Okay, and it still has the same property. So alpha f on alpha 1 on y1 is identically 1. Alpha f on y2 is identically 0. And this means that this averaged function alpha f separates the images of y1 and y2. Okay. Alpha f separates pi of y1 and pi of y2. Hence, the intersection is also empty. Okay, there we are. So this is the end of the proof of the lemma, and now we can finish the proof of theorem 3. So recall that the projection pi from X to X modulo G is G equivariant. And so the preimage of any point, say Z, is a union of G orbits. But we want to prove that it's a single G orbit. That this fiber is a single G orbit. Otherwise, there are two G orbits, say y1 and y2 inside this fiber that do not intersect. But then by lemma, we just proved their images have to be disjoint again. But in fact, there's a contradiction. Since both pi of y1 and pi of y2 are just the same point z. Okay, so there we are, and the theorem is proved. But let me just make another remark that so for reductive groups, more general than just finite groups, we can also define the quotient as the spectrum of the invariant ring and this is called the categorical quotient. And denoted x double slash g. Okay, and now it will not be true anymore that the fibers of the natural projection from x to the categorical quotient are not in general just the orbits. For example, we already discussed it last time. Let me just repeat from the last time. So X will be the space of matrices, or just GLN, and G will be just GLN, the corresponding group, and the action will be just by conjugation. G of A is GA G inverse. So then it is known that the invariant, the space of invariant functions is generated by the traces of powers. This, and so, and in fact, there are no relations whatsoever. It's freely generated. So maybe let me write it down like this. Just the polynomial algebra. So GLN categorical quotient with respect to the general linear group is just some vector space, n-dimensional vector space. Okay, and pi associate to a matrix, just the roots of its characteristic polynomial, the eigenvalues with multiplicities. Okay, so from this point of view, sigma is just the space of monic degree n polynomials. Okay, and so we see the fibers are more than the orbits. The orbits are classified by Jordan normal forms, and here we have some coarser stratification just by eigenvalues of characteristic polynomials. But well, let me write it down. So the orbits, the fibers of pi may contain many g orbits. But what is a general observation that any fiber contains a unique closed g orbit. So these are semi-simple matrices or linear operators. Okay, the ones without Jordan blocks. Okay, and I think maybe that's it for today. So eventually we'll prove this claim. So far I only announce what will be true in general. So for finite groups, once again, the fibers of the morphism to the categorical quotient are exactly the orbits. For infinite reductive groups, this will be not quite so, but still something of the sort will be true. So this categorical quotient does bear some resemblance to the ideal quotient we would like to have. Okay, so I think that's it for today. Any questions, maybe?
Professor, may I ask if there is any reference book for this course?
Yeah, that's a good question. So there are some official reference books in the syllabus, but they have, unfortunately, little to do with reality because they have to be taken from some electronic resources of HSE, and only a book by Chris Ginsburg was there and Dolgachev. And what is more relevant is maybe a book by Springer, Tony Springer, Invariant Theory, and also maybe a survey by Winberg and Popov, also Invariant Theory. I think I will send you the references in the mailing list. And in fact, I'm following just lecture notes of Ivan Losev, who gave a similar course some 4 years ago, I think. And at least that's true for the first half of the course. Then maybe starting from March, we'll deviate. But till March, this will be pretty much a repetition of Losev's course. Okay. Any other questions?
Thank you.
Welcome. So if not, then see you next Tuesday. Bye-bye.
Thank you.
Thank you. Thank you.
Welcome.